Today we are in section 8.6, which is on exponential growth and decay, which is mostly exponential related, but that does tie into logarithms because logs are just another form of an exponent. Okay, exponential growth is what we're starting with. Exponential growth occurs when a quantity exponentially increases over time. This is our formula. So we have f of t is equal to a times 1 plus r to the power of t, where a is the initial amount, r is the growth rate as a decimal, t is time, and t is time. Example 1. The original value of an investment is $1,800. Write an exponential function to model the situation if the value has increased by 7% each year. Then find the value of the investment after 15 years. So just to reiterate here, we had f of t is equal to a times 1 plus r to the power of t. So that's our base form here. Now we need to plug in our values. So we have f of t is equal to, what is the initial amount? 1,800. So we have f of t is equal to 1,800 times 1 plus, what is our rate?
0.06.
7%, which is 0.07. To the power of 15, because we have 15 years. That is our format. Now we're going to find that value, so we're going to calculate that out. So on the calculator, I have 1.07 to the power of 15 times 1,800, which tells me I forgot to plug 15 in here, so we'll do that now. Here we go. So f of 15 is equal to 4,966.26, and this is a value, so that's dollars. Exponential decay occurs when a quantity exponentially decreases over time. Not increases, decreases. We'll just fix this. Is that correct on your papers? Decreases? Okay. All right. In the formula, we have f of t is equal to a times 1 minus r to the power of t, where a is, again, the initial amount, r is the decay rate as a decimal, and t is time. So example 2, an investment is, or of $12,000 is losing value at a rate of 4% each year. Write an exponential function to model the situation, then find the value of the investment after 9 years. So we had that function for exponential decay, f of t is equal to a times 1 minus r to the power of t. What was the time frame that we're looking at? 9 years. The initial amount was $12,000 times 1 minus the decay rate was 0.04 or 4% to the power of 9. So we're going to solve that. 8,310.41. That's what we got. So after 9 years, we went from $12,000 to $8,000. All right, compound interest occurs when interest is calculated on both the principal amount and the accrued interest thus far. The formula, a is equal to p times 1 plus r divided by n to the power of n times t, where p is the initial amount, R is the decay rate as a decimal. Wait a second. Did I forget to change that? That should just be rate in general. Okay. Yeah, R is just rate in general. N is the number of times that is compounded every year, and T is time. I just, for some reason, put decay rate again, even though I didn't. There we go. This is a part of financial math, yes, but financial math does do a little more than just this. Okay. So, some things to notice. While some of our variables changed, the initial amount still goes in front of the parentheses. We still have 1 plus the rate, but now we're dividing the rate by the number of times it's compounded. And we're still going to the power of t, time, but it's the number of times compounded times the time. That's what's happening here. So in example 3, we have 2 parts here. Part A, Laura deposited $12,000 into an account that earns 8% interest. If the interest is compounded quarterly, how much money will she have in 5 years? Okay, so first I'm going to rewrite that general basic formula up here. So I have A is equal to P times 1 plus R over N to the power of N times T. Mm-hmm. N is the compounded number of times compounded. A would technically be amount, but
So, how much, if it's compounded quarterly, like what are the units for that?
So let's start with what we have. A is equal to the initial amount, which was 12,000, times 1 plus the rate, which is 8%, 0.08, divided by the number of times it's compounded. It says that it is compounded quarterly. Quarterly tends to mean every 3 months or 4 times a year. So we would divide by 4. So the power of n, which is 4, times t, which is 5. So if we simplify this, that means we have 12,000 times 1 plus 0.08 divided by 4. What's 0.08 divided by 4? 0.02.
Wait, it's 0.08.
Yeah.
My bad.
To the power of 20. So in the calculator, we're going to type in 1.02 to the power of 20, and then we're going to multiply that by 12,000, and that gives us how much money in the account after 5 years. So because of the quarterly compounding interest, in 5 years, she gained about $5,000. That is pretty good. Part B, Jack moved 25% of his savings to a new investment account that earns 4.5% interest compounded monthly. Find the total amount in the account after 6 years. Okay, so we have A is equal to the initial amount, 25,000, times 1 plus, what's the interest rate? 0.045 over, okay, it says it's compounded monthly. So how often? 12 times a year. So the power of the number of times compounded, 12 times the number of time, or the amount of time, which is 6 years. All right.
What's your favorite number? 72?
Mm-hmm.
That's a good number.
Okay. So then if we simplify this, we have 25,000 times, what's 0.045 divided by 12? So we have 1.00375 to the power of 72 is what I heard. Okay. If we calculate that out, then in the account after 6 years, we have approximately how much? 32,732. Okay, so $32,732.58. All right, continuous compound interest. The formula, we have A equals P times E to the power of R times T, where A is equal to the amount, just like before, the future value. P is the principal or the initial value. E, we should know, R is interest rate, and T is time. Example 4, Lindsay invests $1,000 into an account with 4% per year continuously compounded interest. How much will she have after 10 years, and how long will it take for her investment to double? Okay, before we do anything, I'm going to rewrite that equation up here again. So I have A is equal to P times E to the power of R times T. So looking at this example, we have an initial value of what? $1,000 times E to the power of, what's our rate?
0.04.
0.04 times our time, which is 10 years. Which is, yeah, just 0.4. So we have 1,000 times E to the power of 0.4, which gives us what amount?
It gives you $1,191.4697.
Oh, it was 491 or 941.
What? 1,491.
So I heard the correct numbers and flipped them around for some reason.
Imagine
Yeah.
if you worked at the bank, they would be real happy.
The bank would be happy.
Because you wouldn't have us to correct.
The customer wouldn't be happy. All right. What amount to the nearest cent will an account have after 10 years if $175 is invested? Oh, you're right. How long will it take for her investment to double? That part is actually slightly okay. So if we want her investment to double, then how much do we want the amount to be? 2,000. We have 2,000 is equal to the initial amount, 1,000, times e to the power of 0.04 times t. Okay, we're solving for t. So we are going to use a logarithm. So we're going to start by dividing out 1,000. So we have e to the power of 0.04 t is equal to 2. We're going to convert this to a log. So we have base of e, which means what kind of log do we have? Natural log. So I have the natural log of the answer, which is 2, is equal to the power 0.04 t. How do we get t by itself? Divide both sides by 0.04. So then t is going to be equal to what?
Is it around
17.333 years. Now we'll do part B. Part B. What amount to the nearest cent will an account have after 10 years if $175 is invested at 6.5% interest compounded continuously? So we have A is equal to, says we have initial investment of $175 times e to the power of the rate, which is 0.065, times time, which is 10 years. So then we have 175 times e to the power of 0.65. What does that give us as our amount? We have $335.22 after 10 years with a continuous compound interest of 6.5%.
That's like
That is where we are going to stop today. And that is actually the end of our unit.